Hey everyone, eigenvectors and eigenvalues belong to the most important topics in the linear algebra with a wide range of applications. Welcome to this introduction to eigenvectors, eigenvalues, and their applications. Let A be a square matrix. If A times V is equal to lambda times V with a non-zero vector V and the scalar lambda, then we call V an eigenvector associated to the eigenvalue lambda. Note that if V is the zero vector, the equation is useless, therefore only non-zero vectors. Let us have a closer look at the basic equation and mathematical definition. Recall that matrix vector multiplication is just a linear transformation applied to the vector. Hence, we apply a linear transformation represented by the matrix A to the vector V and get the same vector just multiplied by a number. V and A times V are parallel. Certain exceptional vectors V are in the same direction as A times V. Those are the eigenvectors. The set of eigenvectors associated to lambda is a linear space called eigenspace of lambda. The scalar lambda can be real or complex. It tells us to which extent the special vector V is stretched or shrunk when it's multiplied by the matrix A. We consider a numerical example. We verify that A times V is 3V. Hence, V is an eigenvector that matches the eigenvalue 3. Vectors in the span of V are eigenvectors that match the eigenvalue 3. Multiplication by the matrix A, just scale them by 3. They remain in the span of V. Indeed, span of V is the eigenspace of 3. A similar computation shows that 1 is also an eigenvalue and its eigenspace is the horizontal axis. They prominently arise in various application areas. Let us consider rotations and reflections, which belong to the group of Euclidean motions. Vectors living in the axis of rotation remain unchanged. They are eigenvectors for the eigenvalue 1, denoting the rotation matrix by A. AV is V. Finding the axis of rotation reduces to the task of computing an eigenvector associated to the eigenvalue 1. What about reflections? Vectors U in the reflection plane remain unchanged while any vector V in the axis of reflection flips. The axis is the eigenspace of -1 and the plane is the eigenspace of 1. Indeed, any 3D reflection can be represented by a matrix having 1, 1, and -1 on its main diagonal and zeros elsewhere. For applications, you need to compute them. This requires familiarity with the identity matrix, systems of linear equations, and determinant. It is the topic of the next video. See you then.